Welcome to the High Voltage AI podcast. This deep dive is part of a special week-long series featured in the High Voltage AI newsletter on Substack. We're exploring how artificial intelligence is fundamentally reshaping the electric grid. I mean, really, from that crumbling 20th century infrastructure all the way to a fully autonomous future. Today is Friday, and our focus is the road to an autonomous grid, successes, lessons, and the path forward. Now, to truly understand this journey, this road ahead, we first really need to grasp the immense challenges. These are the things making this transformation not just, beneficial, but absolutely necessary.
Yeah, what's fascinating here, I think, is that the problems facing our electric grid are just so profound. They genuinely compel us to rethink its very architecture. We're looking at a truly fundamental shift here, not just, slapping on some incremental upgrades to the system we have. It's a complete rethinking, really, of how power is managed and distributed. And this means moving beyond just relying on sheer brute force capacity.
Right, just building more stuff.
Exactly. Towards a system that prioritizes intelligent, dynamic control. That's the key.
Okay, let's unpack this then. Because the grid that, powered the last century, it's really groaning under 21st century demands, isn't it?
Right.
It simply wasn't built for a world with massive artificial intelligence data centers, millions of electric vehicles, or, frankly, the increasing fury of our climate. We're not facing just one problem here. It feels more like a perfect storm of converging crises, all pushing it to its limits, operationally and physically. It's this confluence of pressures that demands a truly new approach to grid management.
And if you look at the bigger picture, the traditional utility response, which has typically been, as you said, just build more capacity, add more power plants, more transmission lines, well, that's becoming economically and logistically untenable. It really is. That old approach just can't keep pace with the kind of exponential growth in demand we're seeing now, or, the complex dynamics of new energy sources coming online. This new reality, it demands a strategic pivot, moving away from just adding physical assets.
More poles and wires.
Yeah, exactly. Moving towards intelligently optimizing what we have and transitioning to that system of intelligent dynamic control.
Okay, let's delve a bit deeper then into the physical state. Because the backbone of the U.S. power system, it's really showing its age. I mean, dramatically. The American Society of Civil Engineers, or ASCE, in their most recent report card, they gave the nation's energy infrastructure a C- grade. A C-.
Wow.
Yes, citing the urgent need for significant investment. And this isn't just some abstract grade, right? It's tangible. You can see it in the components. We're talking about a staggering 70% of U.S. transmission lines and power transformers being over 25 years old. Many are operating way beyond their intended lifespans.
That's incredible.
And similarly, 60% of the grid's circuit breakers, these are crucial for safety and reliability, they're over 30 years old.
Yeah.
That's a truly sobering figure when you think about it.
It really is. And the consequences of this systemic aging, they're becoming increasingly apparent. They directly impact every one of us, The U.S. now experiences more power outages than any other developed nation. And what's particularly concerning, I think, is that how long they last, the duration. It's increasing significantly.
Right. It feels like they last longer now.
They do. For instance, between 2014 and 2021, the average time folks were without power during an interruption nearly doubled. It climbed from under 4 hours to over 7 hours.
7 hours. Wow.
Yeah. And these prolonged outages, they carry a steep economic price tag. Estimates of the annual cost to the U.S. economy, they range pretty widely, but somewhere between, say, $28 billion on the low end, up to maybe $169 billion.
That's a huge range, but even the low end is massive.
Absolutely massive. And beyond those direct costs, repairs, lost business, older systems also suffer from significant inefficiencies, just energy loss during transmission and distribution, which ultimately translates to increased costs for consumers. It hits us right in our utility bills.
Okay, so while the grid's physical capacity is strained just by age, it's simultaneously getting hit with these new, huge, and very concentrated loads it was never, ever designed to handle. I like your analogy earlier. Like an old highway suddenly has to handle 10 times the traffic, but all crammed into just a few lanes.
That's a good way to put it.
And this demand tsunami, it seems driven by two main things. That explosion in data processing for artificial intelligence,
Right.
and the accelerating shift to electric transportation.
Right.
These aren't just small increases, they're entirely new categories of demand piling on.
Exactly. And the rise of artificial intelligence is, well, a principal driver of this new intense demand. Data centers, the physical homes for artificial intelligence and cloud computing, they're truly voracious consumers of electricity,
Yeah.
just unbelievably hungry for power.
I've heard some crazy numbers.
Yeah. Well, to give you some context, in 2023, they accounted for about 4.4% of total U.S. electricity consumption. But multiple analyses project this figure will surge dramatically. We're talking somewhere between 9% and maybe 12% by 2030.
Wow, potentially tripling in just a few years.
Potentially. And the energy intensity of artificial intelligence workloads is a key factor here. Think about this. A single internet search powered by an advanced AI model. It needs about 10 times the electricity of a traditional search.
10 times for one search.
Yep. And this demand isn't just large overall, it's highly concentrated. You have single data center campuses asking for power loads in the gigawatts.
Gigawatts, that's like a whole power plant for one campus.
Pretty much. A scale that can literally overwhelm local and regional distribution systems. It forces these massive, rapid grid upgrades that are, frankly, really hard and slow to achieve.
Okay, so that's the AI side. Then simultaneously, you've got the electrification of transportation, putting this entirely new kind of demand on the grid, something that, barely existed a couple of decades ago. The Edison Electric Institute, they project that the number of electric vehicles on U.S. roads will swell to over 78 million within the next decade.
78 million.
Yeah, that's a 1,600% increase from the 4.5 million electric vehicles we had in 2023. Just a staggering jump.
It really is.
And each electric vehicle represents a significant new load, right? Especially when you consider how people usually charge them.
That's the key point. Unmanaged charging.
Exactly. Unmanaged charging, especially when drivers plug in during those evening peak hours, after work, that can effectively double a household's electricity consumption right then. And more critically, this can strain those local distribution transformers, the ones maybe on your street corner, way beyond their design capacity.
Which shortens their lifespan.
Drastically shortens their lifespan and increases the risk of, widespread failures right there in neighborhoods.
Yeah.
Okay, so aging assets, demand tsunami.
Mm-hmm.
What's the third big stressor?
Well, the third major stressor is more architectural. It's about how the grid was built.
Right. You mentioned the one-way street problem earlier.
Exactly. Historically, the North American grid was engineered for a one-way flow of power. You had large centralized power plants, fossil fuel, nuclear, that were dispatchable, meaning you could turn them up or down. Power flowed out across high voltage transmission lines, then down to us, the passive consumers at the end. Very top down.
Simple enough, again.
In theory. But the energy transition we're in now fundamentally upends this entire model. The integration of variable renewable energy sources, VREs, we call them, like solar and wind. It introduces intermittency and unpredictability, things the legacy grid is just, ill-equipped to handle.
It wasn't designed for power coming back from millions of places, or a power that stops when the sun goes down.
Precisely. It's like trying to navigate a complex, multi-lane highway, but with traffic lights that just randomly go out, or suddenly turn green everywhere at once. And this variability, it creates profound challenges for maintaining the grid's really delicate balance of supply and demand. That balance is absolutely essential for stable frequency and voltage.
If supply doesn't match demand second by second, things get unstable fast.
Exactly right. It leads to outages. This dynamic is famously illustrated by the duck curve. You've probably seen charts of it.
Yeah, where solar power pushes demand way down during the day.
Right. High daytime solar generation pushes down the net demand, what the grid needs from traditional plants. But then it surges dramatically in the evening as the sun sets, people get home, turn on lights, appliances, maybe charge those electric vehicles.
Creating that steep ramp-up need.
A massive ramp-up need. And this phenomenon, it's actually evolving into an even more severe canyon curve in some areas with lots of solar. It creates these huge ramping needs that place immense stress on the grid's traditional generation assets, those plants that have to suddenly pick up the slack.
So the grid is now fundamentally a two-way street, like you said. Millions of points of generation, millions of points of consumption, all interacting.
But it's still governed by the traffic rules of a one-way highway. And that leads to congestion, instability, inefficiency, you name it. And if we step back and look at the broader implications, these forces, the aging assets, the explosive demand from electrification and data centers, and this architectural challenge of integrating variable renewables, they don't exist in isolation, do they?
No, they definitely interact.
Their effects are profoundly multiplicative. It's a synergy, but not in a good way here.
Right. Like that aging transformer you mentioned, it's already vulnerable.
Exactly. And it becomes exponentially more vulnerable to the new kinds of stresses from, say, a whole cluster of electric vehicles charging at once nearby.
And a grid that's already strained by that demand tsunami.
Is far less resilient when hit by the physical impacts of extreme weather events, hurricanes, heat waves, wildfires, which themselves are increasing in frequency and severity because of climate change.
And you layer on top of that the ever-present threat of sophisticated cyber attacks, especially as the infrastructure gets more digitized.
It all converges. This convergence of crises makes it undeniably clear that just making incremental upgrades, tinkering around the edges, it's just not sufficient anymore. The old model is fundamentally broken. It can't cope.
So putting it all together, what does this mean for you listening right now and for the future of our power? I mean, the old model is clearly broken. It just can't handle these 21st century realities. Which raises, I think, the crucial question for us as we consider this road to an autonomous grid.
Right.
What does the new one look like? And maybe more specifically, what role will intelligence, and by that we really mean artificial intelligence, play in building this new, resilient, adaptive grid we desperately need?
Yeah, that really is the pivot point, isn't it? Because artificial intelligence isn't just some buzzword here. It's rapidly emerging as the indispensable brain, eyes, and hands for this aging system that's now facing completely unprecedented demands. It allows us to move beyond simply building more, like we used to intelligently optimizing everything we already have and everything new we add to the system.
Okay, so where are we seeing AI making the most immediate, maybe the most profound impact right now? Is it more about making the existing infrastructure last longer, or is it about managing all these crazy new demands?
Well, the interesting thing is it's both. And often they happen simultaneously. One of the most critical areas, I'd say, is predictive maintenance and asset management.
Getting ahead of failures.
Exactly. Right now, utilities often operate on a reactive model, right? Something breaks, then we fix it, usually after the power's already out. But artificial intelligence, with its ability to process just vast amounts of data from sensors, we're talking everything from temperature and vibration to power flow, oil quality, and transformers. It can predict failures before they happen.
Like a crystal ball for grid components.
Sort of, yeah. Imagine knowing that a specific transformer on Elm Street is likely going to fail in, say, 3 weeks because its operating temperature is showing a weird anomaly, or that a particular circuit breaker is degrading faster than expected.
That would allow for proactive repairs, wouldn't it? Instead of waiting for it to blow.
Precisely. It allows for planned proactive repairs, which dramatically reduces those unexpected outages. This isn't just about efficiency, though it is more efficient. It's fundamentally about reliability for everyone. We can move from costly, disruptive emergency repairs crews scrambling in the middle of the night to planned, efficient maintenance during regular hours. And this also strengthens the grid's overall resilience, helping meet those N-1 contingency requirements, making sure that if one component fails, the system can seamlessly pick up the slack without impacting service.
That really sounds like a potential game changer for cutting down those 7-hour power interruptions you mentioned earlier.
It definitely has that potential.
Okay, so that's keeping the old stuff running better. What about managing those enormous new loads from AI data centers and all those electric vehicles and dealing with the intermittency of renewables?
Right, this leads us straight into dynamic load balancing and demand-side management. This is where artificial intelligence truly shines, I think. It's like an orchestra conductor for this incredibly complex dance of supply and demand.
Conducting the duck curve, basically.
In a way, yes. The duck curve isn't just a graph. It's a daily operational etic, a real challenge. Artificial intelligence can analyze real-time grid conditions, look at weather forecasts predicting sun and wind, and even predict consumer behavior to balance the grid dynamically, second by second. It can, for instance, incentivize electric vehicle drivers, maybe through dynamic pricing signals sent to their chargers, to charge during off-peak hours when renewables are plentiful and cheap.
Or coordinate charging across a neighborhood.
Exactly. Intelligently coordinate charging block by block to prevent those local distribution transformers from getting overloaded. And for those huge data centers, artificial intelligence could potentially manage their power consumption more flexibly, perhaps shifting non-critical computing workloads to different times or even different geographic regions where renewable energy is abundant at that moment.
Creating a much more flexible and grid-friendly demand profile from these massive users.
That's the goal. It's about making demand responsive to supply, not just the other way around.
So it's not just about producing more power, like the old way, but intelligently shaping when and how we use the power we have. That sounds like it connects really well to ideas like virtual power plants and managing all those distributed energy resources.
Absolutely. Artificial intelligence is essentially the only tool capable of orchestrating those millions of distributed energy resources. Things like rooftop solar panels, home battery storage, smart thermostats, even controllable appliances into a cohesive, functional virtual power plant. It can predict solar generation hours, even days in advance. It can figure out the optimal time to charge or discharge a battery to support the grid. Basically, it turns what was once a liability, the intermittency of renewables, into a flexible asset that can respond almost instantly to the grid's needs. This helps avoid those massive ramping events that put so much stress on the traditional power plants.
Okay, efficiency, flexibility. That makes sense. But beyond that, there's always the shadow of cyber attacks, especially as our infrastructure gets more digital. What role does AI play in keeping the grid secure?
That's another crucial area, enhanced resilience and cybersecurity. It's a double-edged sword, right? As the grid becomes more digitized and interconnected to enable all this smart stuff, it also inevitably becomes more vulnerable to sophisticated cyber threats.
A bigger attack surface.
A much bigger attack surface. Artificial intelligence can act as a sort of vigilant, tireless guard here. It can continuously monitor network traffic, operational data from systems like SCADA, looking for anomalies, subtle patterns that might indicate an intrusion or malicious activity. It can potentially detect things that human operators, overwhelmed by data, might miss, identifying and even helping to isolate threats like intrusions, aiming to disrupt operations or steal data.
If something does get through, or there's a physical disruption like storm damage.
Well, that's where AI's potential for enabling self-healing grid capabilities comes in. In the event of a disruption, physical or cyber, artificial intelligence could potentially automatically reconfigure the grid, rerouting power around the damaged or compromised sections, isolating the problem to minimize the impact and duration of the outage.
Faster restoration, less widespread impact.
Exactly. This kind of capability is absolutely critical for achieving a truly resilient and ultimately autonomous grid.
Okay, so we've talked about these incredible potential applications: predictive maintenance, dynamic balancing, virtual power plants, cybersecurity. It sounds amazing.
Yeah.
But building an autonomous grid isn't just flipping a switch, right? What have we actually learned from the early deployments? And what challenges still lie ahead on this path forward?
That's a really vital part of the lessons learned piece. And you're right, it's definitely not just flipping a switch. We have seen some really encouraging early successes in pilot projects and initial rollouts. For example, I know of a utility out in California that managed to reduce outages by about 15% just by using artificial intelligence for predictive maintenance on certain key assets.
50% is pretty significant.
It really is. And another one down in Texas improved their integration of renewable energy. They could handle more variability from wind and solar using AI algorithms to manage the system, allowing more megawatts of clean energy onto their grid reliably. But, it's not a silver bullet. Not yet, anyway. I think maybe the biggest lesson learned so far is the absolute critical need for high-quality, standardized data.
Garbage in, garbage out, basically.
Pretty much. Artificial intelligence is only as good as the data it's fed. If you have inconsistent data, missing data, noisy data, the algorithms won't perform well, or worse, they might make bad decisions. Another huge challenge is interoperability. You have all these different systems, different sensors from different vendors, different utilities with their own legacy platforms. They all need to be able to talk to each other and share data seamlessly.
Breaking down the silos.
Exactly. Regulatory bodies like FERC, the Federal Energy Regulatory Commission, they're increasingly issuing orders and standards to try and encourage this. And there are initiatives, like the PXRD model, trying to establish common frameworks for data exchange. But it's a slow process.
What else?
Well, then there's the workforce challenge. This is a big one. We need to reskill existing utility workers, the operators, the engineers, the line workers, and also train a whole new generation to operate and maintain these highly intelligent, data-driven systems. It's a different skill set.
And trusting the machines.
And finally, yes, the human element. Building trust in these autonomous or semi-autonomous systems. Grid operators need to understand at some level how the artificial intelligence is making its recommendations or decisions, especially when critical infrastructure or even human safety could be at stake. We need transparency, explainability. That's crucial for adoption. Looking back at the big picture, all those forces we talked about, the aging assets, the exploding demand, the shift to renewables, they don't exist separately, right? Their effects multiply. But the key insight here, I think, is that artificial intelligence, with its unique ability to process, predict, and optimize at speeds and scales that humans simply cannot match, it offers a fundamentally new way to manage this incredible complexity. You could argue it's the only thing agile enough, powerful enough to help us effectively re engineer an entire century's worth of infrastructure, almost in real time, while keeping the lights on.
So while the challenges are definitely immense data, interoperability, workforce, trust, it really does seem like an AI-driven autonomous grid isn't just some far-off vision anymore. It's becoming that indispensable brain, eyes, and hands for this aging system facing these unprecedented 21st century demands. The real aha moment here for me isn't just that we need artificial intelligence, but the realization that its unique kind of intelligence might be the only thing agile enough to actually pull off this massive transition, to re-engineer a century of infrastructure on the fly. Which leaves us, I think, with a really compelling thought to ponder. As we inevitably hand over more control, more decision-making to these powerful intelligent systems, how do we ensure that the human element, our judgment, our values, our oversight, remains absolutely vital in shaping this truly autonomous future? How do we keep the human in the loop effectively? This exploration has been hugely valuable, I think. Hopefully giving you listening a much clearer understanding of the forces at play and the really indispensable role artificial intelligence is starting to play.
Yeah, and it raises an important follow-up question, doesn't it? Considering the sheer scale and the interconnectedness of all these challenges we've discussed, what unique demands will be placed on the artificial intelligence solutions themselves as we move towards a truly autonomous grid? It's not just about applying any AI, it's about developing AI that's robust, secure, and capable enough to handle this unprecedented complexity and criticality. That's a whole challenge in itself.
Absolutely. Well, we hope this deep dive gave you some real insights into the road to an autonomous grid. If you'd like to leave feedback or have any questions, feel free to reach out to our producer, Julius Guay, that's Guay, pronounced Guay on LinkedIn.